So, tired of seeing me yet?
You want the real answer?
Yeah.
Never.
Woo! All right. Let me do my yoga thing. We'll all do the yoga at the break. How many people here know about vector tiles? Is this like a understood thing? So we got a sort of 50% quorum on the conceptual idea of a vector tile. I think it's worth talking about vector tiles from the very beginning, because I think it's actually really interesting, because I am a massive map nerd. I assume most of you are massive map nerds. And we have, by and large, lived through this wonderful history of taking maps from a thing which is a physical artifact which you carry around in your hands to a thing which is dynamic and live and you carry around in your pocket. And that history travels through tiles a lot. So the computer map, the original computer map, that most people were familiar with, was a tile-based system. MapQuest dealt with the problem of doing a tile-based system. And they did it because, this is late 90s, early 2000s computing power. Computing cycles are expensive at the time. The amount of bandwidth you can push down your dial-up connection is small. This is the dawn of web mapping, and it's really kind of an ambitious idea, right? We're going to take all the data for initially the states and then the whole world, and we're going to generate viewable maps of it. So there's this huge data processing problem. It's not something you can do live because you have to deal with the corpus of the entire country, the entire world. So you want to do it ahead of time, but you still want to be able to provide people somewhat random access to this map. So what do? They generate tiles. And each page view will give you the appropriate tile for the zoom level and tile center that you are interested in. Render once, great big tile cache. Everything is static. The page is static. The tiles are static. Therefore, everything is cacheable, so you get the fastest response you can. One big difference to modern map tiles is that the map viewer here shows you one tile at a time. And if you want to see the next tile, you click on the appropriate arrow to go up to the next tile, or left or right or down, or if you want to go zoom in and out, you get a different tile. But each time it's one tile. And that was fine if you knew ahead of time what you were going to show. And MapQuest knew what they were going to show, right? We're going to show them a roadmap, and then we'll maybe show them points of interest. But most of these, we're going to show them a roadmap. And that kind of left us GIS people out in the cold. But fortunately, processing power got better. And then the question became, for sort of arbitrary people who hold spatial data, how do you get that information out there? And sort of the second round, circa 2000, and for the next 5 or 6 years, was this idea of dynamically rendering the data. So in this case, you're thinking, well, I got a database full of data, or I've got a shapefile full of data. And what I'll do is, given the request from the client for a particular extent, I will take the raw data, color up, and send them back a picture live. And that was the principle behind ArcIMS. There's the principle behind the Open Geospatial Consortium WMS specification. CPU cycles were cheaper, so it was possible to render a whole map view on a go and send it back, and for people to see the new map without them getting bored and walking away from their computer, mostly. Not pre-rendering everything was great for the kinds of use cases these folks were managing, which was, I maybe have 2 people a day coming to look at my data. Well, it's not a lot of sense in pre-rendering a whole tile cache, because storage ain't cheap either. If you're just going to have 2 people look at it, it's better to just live render your raw data. So it kind of fit in nicely to that use case. But it's one big rendering. So from corner to corner, that's one big rendering, and you would choose the next rendering. It gave you lots of flexibility about what you're looking at. Kind of fit nicely to the ArcIMS idea of ArcView on the web. But not a great model for the mass market, the MapQuest market. And then, 5 years after sort of the move into dynamic maps, we got the day the earth changed, right? 2005 was the public beta release of Google Maps, simultaneously displaying unbelievable computing acumen and design acumen actually as well. They really changed the way people did cartography on the web with their renderings of this map. But they also, just the naivete of, here's our map. Notice that it stops below Mexico. Yeah, the original Google Maps was just North America, nothing else. Even better than that, we've gotten used to Web Mercator, right? Everyone's used to, okay, Web Mercator, fine. They're not geodesists. They did Web Mercator. For the first release of Google Maps, they didn't even do that. They just applied a single scaling number, I think it was like 1.6, to the latitude, longitude coordinates. So it's more or less conformal in the lower 48, but you can start to see it squish as you get up there into the northern parts of Canada because it's a single scale. It's not actually a Mercator projection. So yeah, it's this like incredibly naive thing, but at the same time, they sort of cracked this problem of how to make a dynamic feeling map that I can serve to 100 million people at the same time. And the answer was we go back to tiling. We use more of the smarts that now exist in the clients, the fact that the desktops are powerful enough now to run small programs in the desktop right inside the web browser. And then we send back the map not as one big tile like MapQuest, and not as a dynamically rendered map filler as ArcIMS and WMS, but as literally a tiling, a collection of tiles. So that map would consist of maybe 9 independent tiles. And everyone was quite taken with that because they thought how fast it is. Like, oh, this map is so quick, it's so responsive, it's so much better than these dynamically rendered maps. But one of the things you noticed, you sort of timed it out, was that because it was tiles, you start to see the first tile almost immediately. But it would take a while for all 9 to come in. So we actually timed the time between first tile to last tile and compared that to the dynamic rendering time. Turned out that it was more or less the same. The extra speed of the new Google thing was kind of an illusion, but illusions are good enough. It felt fast. So now you have a fully cacheable map, so you can serve up stuff really, really fast. And then right after 2005, you got into, there it is right there, red dot fever. All these people who'd never had access to a base map before were super excited about the ability to put another layer on top. Because if you'd done one of those old school maps right here, if you were in a county government and you had to build a web mapping server, you'd very, very quickly learn that building a web map was a hell of a lot of work. Because it wasn't just putting the thing you cared about, the fire departments, fire stations on the map, right? A map of fire stations is no good because it's just, 10 points. It's only useful if you put all the other stuff on the map. So you've got to get the roads, you've got to get the land cover, you've got to get the water, you've got to put all these things together. You've got to arrange them in a cartographically attractive shape. I mean, building a base map is an immense amount of work. And all of a sudden, Google was there saying, hey, here is a fully zoomable from North America all the way down to the street level map with cutting edge, super attractive cartography, which at this point we're giving away for free. And people just went, whoa, red dots everywhere. It was the new thing. So we had this sort of paradigm shift. Before 2005, there was this idea, the IMS, WMS idea, which is a map consists of a whole lot of layers, and you have to stack them all up and color them separately and make them look like a big map, and you serve that whole pile of layers back in one big swath. And after 2005, you kind of realize, oh, wait a second, no, a map consists of 2 layers, just 2. It consists of the base map and the thing you care about. That's a big change. Because the base map, which is the really, really hard thing to build, you only have to build once, and you can cache it because it very rarely changes. Your thing of interest probably changes quite a lot. Maybe you want to render that dynamically. And people did render it dynamically, initially just using JavaScript. But you can render more complex things, more than just markers, lines and polygons, colorization. All that stuff is available to you, and you only have to think about that one layer, and the rest of it just comes along. The base map is a freebie. So that's what a modern web mapping architecture looks like. You separate it. So I've got my base map, it's static, I'm going to generate it once, I'm going to pre-cache it, it's really, really reusable. There's lots of data. Like that tile is really busy. There is a lot of data embodied in that tile. Parks and roads, all the labeling, which is incredibly complex and CPU intensive to do. But you do it once, you cache it, and it's really reusable. All these apps use the same base maps over and over again. And then you got the layer of interest. Every application has its own separate layer of interest because it has its own separate business concerns it's trying to address. That's the modern web map architecture. And that's what we're going to see, actually. The things I'm going to show you, the things Steve's going to show you later, these are all based on the idea that a modern web map architecture consists primarily of 2 things, the base map and the thing you care about. So The Google world, the Google sort of brain widening was about understanding that they could do global map tile addressing and make it very, very reusable. And three primary schemes have come out of that. The first is Google One, which says that any tile can be addressed by making reference to the zoom level of the tile and its X and Y coordinates within that zoom level. The Bing scheme, which says that any tile can be described by a path through the subdivision of the overall space. So you start and you say, it's start with the left-hand corner, and then inside that left-hand quadrant, left-hand top quadrant. And within that, take the lower right-hand quadrant. Then with that, take the upper left-hand quadrant, And that's the Bing map style. It's basically the same thing, though. It's a quadratic subdivision of the space. And then OGC in its in its wisdom, they did more or less the Google map addressing scheme, but because they were OGC, they decorated it with a million possible options. Unlike the Google and the Bing ones, it supports multiple map projections, so it's very, very configurable. Even worse, it supports the idea of arbitrary zoom layers, so you don't get some of the nice powers of two features of the Google and Bing system. But it is well specified, and lots of open servers support it, so it is a real thing, and it is available for use out there. I mentioned Web Mercator, so here's the magic of Web Mercator. And the magic of Web Mercator, and Mercator in general, frankly, they could have just used real Mercator. They didn't have to do their own thing. But they did. Regardless, they have the same property, which is when you take the whole world and project it in Mercator, the result, in terms of the things you care about, which is to say everything between 85 degrees south and 85 degrees north, is perfectly square. That's really nice. Perfect square, both directions? That's great, because it means it subdivides. It subdivides perfectly, and that's where we get into the idea of a zoom level. And the zoom level this is true for both Bing and Google, and really for most web apps that are working in Mercator world. But even in non-Mercator, you can construct these perfect power of two zoom levels as long as you're willing for your initial sort of zoom level 0 layer to be a perfect square that encompasses the things you care about. And yeah, it's great. 85 south, 85 north, you lose sort of a little circle of Antarctica, but actually all the coastline, you don't lose any of the coastline. That's pretty cool. And then, you've gotten north of Greenland, so you've got pretty much all the landmass of the world there. I think it's this idea of a zoom level, which is super duper. Okay, so zoom levels refer to powers of 2. At zoom level 0, there is one tile, which is to say 2 to the 0th tiles on each edge. Zoom level 1, 2 to the 1 tiles on each edge. Zoom level 2, 2 to the 2 tiles on each edge, and so on and so on and so on and so on. Perfect. Perfect, perfect, perfect. This is great from a subdivision point of view. It's great from a computer science point of view because nothing is cheaper than taking something to the power of 2 or reducing something by a power of 2. It's a bit shift operation. It costs 1 computation cycle. There's nothing cheaper than that. So you can see the assumptions, though, built up here. So assumption 1, we're using Mercator, so we have a perfect square. That gives us, if you translate the world into Mercator, the distance from along the equator from negative 180 to 180 is 40 million. It's negative 20 million in Mercator on the west and 20 million in Mercator on the east. So it's about 40 million across, 40 million top to bottom, in those bounds. So powers of 2. Now we've got our zoom level. Next question is, what do these X and Y coordinates mean in the Google addressing scheme? They refer to the coordinates within the zoom level. So this is zoom level 2 because there's 4 things on each edge. Starting counting from 0, so the top left one is tile 0, 0. Counting out 0, 1, 2, 3. And you can see the parent over there. That's zoom level 1. 2 tiles on each edge. It's kind of hard to explain, but give it a shot. The parent of any of these smaller ones you can derive the coordinates of the parent tile just by dividing the coordinates of the child tile by 2 and throwing away the remainder. So you can, again, at the cost of 1 computation cycle, hop up and down this chain and figure out what the parent tiles are and so on. So this is why the Google people were super excited about this, because it matched their computational minds. These are not cartographers, these are computer scientists, and they're really happy to work in Powers of 2. So Google gives you a tile address. They say, we're at zoom level 2, tile address 3,2. We, geographers, need to work with that in geographic space. That's no good for us. We need to convert that into a geographic extent. But if you know the tile address, as we do, and you know the projection, as we do, and you know the bounds of that projection, as we do, the world, you can take that address and back it out and calculate the geographic extent. And then you can do all the things you need to do in PostGIS land. So Google came up with a lovely idea of this sort of nice quadratic subdivision of the world, and they said, let's do tiles. Next question is, what are you going to send back when you send back a tile? Early implementations sent back PNGs, because that's what web browsers could render. Send back a PNG, the web browser will render it. Lovely. Image formats are great. Web browsers understand them just fine. Either you send back a PNG if you have a cartographic map, because PNG is compressed not really nicely. You want your tiles to be small as possible. So for a cartographic map that has lots of identical colors, PNG is compressed really well. If you're doing imagery, you send back JPEGs, because those compress better than PNGs if you have lots of color gradient. As you get into the modern era, getting towards, I don't know, 2012, you start to see the first retina displays coming into phones. The trouble with a retina display from the point of view of an image is that the image, if it's a fixed resolution, as these things all were, they're all 256 by 256 tiles. A 256 by 256 tile in a retina display starts to get really, really small. And things that have been burned into it, like the labels, get so small as to be unreadable. So around the advent of retina displays, you start to see tile caches having to be duplicated. Now you need one cache at 256 by 256 for standard sort of 72 dpi displays, and you need a second cache at double resolution in order to be able to support retina displays without having people have to hold it up to their eyes to be able to make out what's on the map. So you can start to see some of the cracks appearing in the idea of sending images back. So we got the size. The more resolutions you have, 512 by 512, that's a lot bigger tile than a 256 by 256 tile. So you're sending back a lot more pixels to show the same thing on the screen, and those pixels cost you money because you're stuffing them through the tiny little network pipe to get it down to the cell phone. Images also have the problem that you end up burning in the labels, and you have to choose how you burn in the labels. If you burn in labels onto the base tile, then when you lay something on top of it, the thing on top will occlude your labels, which reduces the legibility of your map. There's a quick trick to get around that. You send back a label-less thing on the bottom, stick your layer of interest in between, and then send back the labels as a top layer with everything else transparent. So now you've got something which is more legible, except now your base map labels might occlude your layer of interest, which is not good. And at the same time, you've doubled the amount of tiles you have to send back just to display the same map. So you're starting to see the cracks appear in image-based map tiling as people's demands for perfecter and perfecter maps keep going up. So enter the vector tile. Around 2010, if you're sort of watching the field, you notice that something's changed. You notice that all of a sudden the Maps app on Android has gotten a lot snazzier. You're seeing the labels resize themselves as you zoom in and out. And even more, you can rotate it and the map rotates with you. And relabels itself. So it's like, oh, something's going on here. This isn't imagery anymore. This is being dynamically rendered on my phone. And that's when people went, oh, wait a sec. Google is now sending back vector tiles to Android clients. And a couple of years later, they started sending back vector tiles to the Google Maps web client as well. And people in the open source world recognized that this was a thing we're going to need. Mapbox was the first out the gate with a full implementation. So they implemented the idea of the MVT, the Mapnik vector tile specification. First implementation, read-write, was in Mapnik. And here's the crazy part about the Mapbox work and the Mapnik vector tile, because it was seeded by people looking at the client implementation on Android and saying, hey, that's vector, that's really cool. That's neat how that works. But that's not what Mapbox used it for initially. What they used it for was just to make their dynamic rendering chain run faster. So what they did was they took raw data out of a database and they chopped it into these Mapnik vector tiles. And they made a vector tile pyramid and they kept it there on the cloud. And then when people were drawing maps for their client, what they would do is they would still dynamically render, but they would dynamically render starting from the vector tile. So it cut out all the overhead of getting the raw data and cutting it into tiles and reducing the precision, all this stuff. So the vector tile was almost all the way to the image format. They just had to apply the styles and spit out the image format in their second part of their chain. So they were still rendering and returning images early on. They didn't actually write clients that were capable of rendering the vector tiles on the client side for a couple years, till a couple years after they had introduced the format. So it was an interesting quirk, because you'd think, seeing the client, the first thing you do is write the client. But they actually got ahead of the game and were able to provide some of the benefits of vector tiles early on without actually delivering them to the client. So there's a lot of steps in baking a vector tile. You get a request, which gives you where in the world it is. From that tile request, you calculate the actual geographic request. Then you pass that back to whatever your data store is, PostGIS if you're a smart, beautiful person. Take that data, the raw data that comes out, and simplify it to the tile resolution, which is generally 4096 by 4096, but sometimes less, sometimes more, depending on your tile desires. Note at this point, it's not raw data anymore. It's been quantized, and sometimes quite heavily. Vector tile formats are more similar to images than they are to raw data. Just like an image, things have been quantized to a much lower resolution than the original, and you've lost lots and lots of information in the process. It's very important to think of vector tiles as a visualization format, not as a data format. If you want the raw data, you need to kind of build a different channel into the raw data than the vector tiles themselves. So you're quantized to the integer grid. That quantization can destroy your validity, and sometimes you have to repair your geometry afterwards. You take the data, make sure it's clipped to the tile bounds neatly. Try to make it as small as possible, so you re-encode your coordinates in tile coordinates. So they're all generated as offsets. Those offsets compress wonderfully when you stick them into the protocol buffer format, which is the file format that wraps the data, and then you send that protocol buffer format back. And there's a few quirks in there. This is quirk number one. You cannot generate useful vector tiles just by clipping the data to the tile boundary. And that's counterintuitive. You think, well, no, I've got two tiles, and if I clip to the tile boundary, the data matches up perfectly on the edge, right? So I can render everything just fine. And that is true as long as your rendering is extremely narrow, at the resolution of your device. If you're rendering something larger, like a thick line or a big icon, and it's right near the edge, part of that rendering is going to be inside your tile, and part of it's going to be outside your tile. And the tile rendering is done a tile at a time. They're completely independent. You pull back the vector tile, you render it, you stick it on the screen. So what the renderers do is they get a little more data than they need. They render into this larger canvas. Then before they put it on the screen, they clip it to the actual boundary, and then they put those up there. And for that to work, you need to get a little bit of extra data, even when the data doesn't even fall inside your tile boundary. So all these tile data requests end up being for slightly more data than the tile boundary itself would seem to suggest, so that you can render wide things, big pixels, wide lines, and so on. If you don't do that, you get little gaps and corners as your line traverses the boundaries between the tiles. You also get bad labeling artifacts. Next step, simplify and quantize. This is basically a space-saving step, because if you stay in double space, all of your coordinates require double precision numbers. That's 8 bytes. If you get down to integer space, boom, right away you're down to 4. If you then take all your coordinates and treat lines as paths where you difference the distance between each successive vertex, you can cut your integer size down to the point where maybe you can encode them in 2 bytes or even 1 byte. It's just a way of making things small, because you want to stuff this thing through a narrow bandwidth pipe. You're stuffing it through like a mobile data connection or something. So you want every tile to be as small as possible. That's the trick they use for that. And then, so this is the way you do it, by doing deltas. They have some rules about winding order, so the renderer doesn't have to make guesses about winding order. It's sort of classic right-hand rule, vector rules for winding order. And then once you've got all the data in that shape, you stuff it into a protocol buffer, which is pretty straightforward for the geometry. You take those funny process geometries and you stick them in. again, trying to make things small. MVT was produced by Mapbox primarily thinking about rendering OpenStreetMap data. And OpenStreetMap data has a very strong propensity towards this idea of tag value, tag value, tag value. It's very repetitive. So the Mapbox guys thought, well, the best way to make this fast is to take every instance of a given tag name and give it a number, and every instance of a value, a various value name, and give it a number, and put these in a dictionary. So we only store the fully spelled out keys and values once, and then store the dictionary numbers everywhere else. That works great for categorical data. It works less great for things like continuous floating point data. By and large, it's still usually a net savings for ordinary data, but it's something to be aware of. If your data consists of lots and lots of continuous floating point numbers, you're going to end up seeing your vector tile get perhaps larger than you expect because all those values are going to go into a dictionary. And then protocol buffers is the actual file format. It's a format that was invented by Google for their internal data transfer needs between their different systems. It is, for the graybeards, very, very similar to what Sun promoted back in the 90s as XDR. It's just a binary way of storing structures. So yeah, dynamic map tile serving. Back in the old days, you do dynamic map tile serving. What you do is you have your database, you stick a big piece of middleware in the middle, and it takes in the request. The database does nothing but feed features back to the middleware. Generally, the middleware says, give me a box of stuff, and the database hands it a rectangle of stuff, and then the middleware crunches on it and either returns an image, in the case of the old image tiling services, or now it will return a tile. Let's not just add big fat middleware. Let's add just a tiny little narrow HTTP layer that takes in the tile request and then uses that request to construct a SQL query that does everything. Everything from getting the data, to clipping the data, to conditioning the data, to the tile format, to actually producing that binary tile format and sending it back. And until PostGIS 3, that wasn't particularly possible, but now it is. If you have XYZ bounds, a Google Map tile address, you can convert that into a geometry bounds using the new tile envelope function, PostGIS 3. Once you have that bounds, you can use that bounds to pull features back and then use the as MVT geom on the geometries to condition them. So that clips them to the boundary, it squishes them down to integers, it flips them to the appropriate image coordinates, it quantizes them down to 4096 by 4096, it adds a little buffer around the tile boundaries, works like a hot damn. Once you have MVT geometries, you can pass the results of that in as the geometry column, and then any other attributes you want as a row into the as MVT function, and that will take the geometries and whatever attributes you included in your row, turn them into a protobuf, and send it back out, which you can then send off to your web client. And this is what, pretty much, yeah, that's all the SQL you need to do a full cycle dynamic conversion of data in your tables to an MVT file. So it's got a CTE up top, which generates the MVT geometries using the MVT geom file and the tile envelope, using the ST-intersects to strip it down to just the geometry of interest. And once it has that MVT geom processed sets of rows, it just passes them into ST as MVT, which is an aggregate function. So it takes in all the rows that come out of MVT geom, aggregates them into one protocol buffer, and sends it back. It's pretty slick. So there's an expensive part, which is the geometry processing. We've got clipping, we've got quantization, we've got point removal, we've got simplification, we've got lots of sort of geometry processing stuff happening in that step. It's pricey. And then we've got a relatively cheap section down here, the format conversion one where you make the as MVT file. That's relatively cheap. The beauty part is, because this as MVT file is an aggregate, Postgres 11, Postgres 12 will happily parallelize this process. So it will do all this expensive geometry processing in parallel threads. So you can heat up multiple threads on your server generating these tiles. I think I have a performance thing here. So I pulled for Vancouver, parcels. There are 100,000 parcels. They were all in UTM zone 10. This is what the query looked like. Because the parcels were in UTM Zone 10, we had to do a little bit of extra stuff compared to the previous SQL. We have to transform the data, transform the output data into Web Mercator, and transform the input envelope into UTM 10. But otherwise, it's exactly the same query as the one I showed. So this is the kind of query you'd run against your real operational data. And then you can see you got a parallel plan. So planning time, execution time, 100 milliseconds. That's querying against 100,000 features, getting a tile back, which consists of 3,000 features in 160 milliseconds. So I know what you're thinking. That's just a lot of slides, Paul. Show me something working. Show me some real software. And yeah, I'm happy to do that. Here's my demonstration architecture. This is just as I described it to you. I want the smallest possible thing between my database and my web client. So the smallest possible thing I can write. So let's see here. What's the best way to do this? I think it might be to take my displays and unmirror them. And then you can see all my stuff. Nice. Okay, so bring that up and make it bigger. No. Oops. There we go. Okay, so this is a Python program. It is this long. I guess the numbers are there. 151 lines. Most of it is boilerplate. In fact, really all of it's boilerplate. But there's the web server part. So this is just from the Python HTTP server module, part of Python 3. All it does is fire up an HTTP server. And this is the only part which is custom. We tell the HTTP server, when you get a request, send it to this object, a tile request handler. So I get this definition for a tile request handler. Request comes in. First thing it does, actually just look at this stuff right here. Here's what happens. Request comes in. It's a Google request, so it's a ZXY request. I want to turn that string, it's just coming as a string, into a tile. So that's just a regular expression. All it does is take in the string and parse out the Z, the X, and the Y components. Right here. String comes in, regular expression parses out the zoom, the X, and the Y, and the format. But it's always PPF. Okay, now I've got the Z, X, and Y. That still hasn't got me down to geospatial world. Where am I? Here it is. So now I'm going to go from that Z, X, and Y straight to the SQL. I think that's not that one, but that one. So here we go. This is really the only thing. Everything else is boilerplate. I'm parsing a string. I got a Z, X, and Y. Little CTE to convert it to bounds. So again, I'm using the tile envelope, zoom, X and Y, taking those bounds, passing them into this thing which returns back a set of process geometries and whatever attributes I want. I can use any SRID that I like for my target table. I convert the output of that to 3857 for clipping, 3857 being Web Mercator. Clip it against the bounds, add any attributes I care about, select it from the table, only the features that intersect my bounds again, and finally take that set of rows and convert them to NVT. So that's from line 72 to line 86, so 14 lines. And that's basically it. I've got the SQL, so then we've got boilerplate. Here's a little function that takes SQL and executes it against the database. So it's really nothing more exciting than execute the SQL, and then a little bit of error handling if things go wrong. Once you get that PBF, you send it back. That's the whole thing. So 150 lines of middleware. When you run it, looks like this. It's not doing anything yet. Now, where's my example? There it is. I'm going to refresh this guy and let it do its thing. Boom, 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 boom. So these are all vector tiles being drawn on. The base map is a raster base map from Carto. You can see their vectors because you can zoom right into them. You can see that they're being demand generated because as I slide along here, I'm getting new ones each time. And if I go over here, I'm logging out. So each time I generate a new tile, I log out the SQL that is relevant to that tile. So here's tile at zoom level 16, 10,000 by 25,000, generating the envelope from that, applying the envelope, getting the geometry, and then the house, street name, all that stuff back. So that stuff is all embedded in the tile as well. I'm not doing anything with it render-wise, but it's embedded in those tiles. And it's pretty damn quick given what it's being asked to do. There are, I think, 500,000 parcels in this set. Is it parcels or parcel? Parcels. Yeah, 500,000 parcels in that set, and that's demand rendering the tiles on the fly. Pretty damn good. That's a demo. That's my talk. Thanks a lot.